Hi, I'm Rendell Heyman, a mathematics academic, and you're on one of my Corona Help playlists where I make quick turnaround videos to help people during the coronavirus outbreak. So if you'd like a video, just comment below any of my videos or drop me an email. So I hope you're well today. Be interesting to see how this one turns out. I noticed the last video I did, my voice sounded very, very low. I think there's some technological bug going on there, but anyway, hopefully this one's better. Just before we do what I want to do today, just mention that in a couple of days' time, I'm doing a Zoom workshop, which you're welcome to join. It's about some interesting aspects of the number 1 plus the square root of 2. So we'll be doing it as a workshop. So people who attend will be working on some mathematics that I'll just direct what people should work on, and hopefully even though there'll be people of different mathematical levels attending the workshop, hopefully at the end of it everybody will walk away having discovered some interesting things themselves. So I've put some times up there, you can see on the screen when it will be. It's not very suitable for people in Europe and Africa. If this workshop goes well, I'll do one next week at a time zone that's more compatible for Europe and Asia. Europe and Africa. If you go back to my the immediately previous video of mine, there'll be a link below where it's got the Zoom link so you can join. So I look forward to maybe seeing you then. Okay, let's rub this out and talk about what we want to talk about. I've had a couple of emails from a high school student, Behsad, who I gather is from Germany, from the internet address, and he's interested in the Euler totient function. Well, in fact, he's interested in some proofs. Now, I do have a video, Euler totient function made easy, where I go through some of the basic rules for the Euler totient function. And I've got some other videos where we start to use the Euler totient function in the real world. What are those videos? Euler's theorem, and then we go on to RSA code, which is encryption and that sort of stuff. So an important function, the Euler totient function. Now, Behsad wants me to do the proof of this, that the Euler totient function is multiplicative. What do I mean by that? I mean, if the GCD of M and N is equal to 1, then the Euler totient function for M times N equals the Euler totient function for M times the Euler function for N. And that's what mathematicians say means that it's multiplicative. Okay, so to do that, we could do it directly, but a better way is to look at the formula for the Euler totient function. So if N equals, so here we've got prime 1 to the power of alpha 1, prime 2 to the power of alpha 2, ... prime k to the alpha k. So this is a fairly standard way of expressing a number n. It'll be the product of primes to various powers, and that's all that I'm writing there. So for example, 60 is equal to 2 squared times 3 to the 1 times 5 to the 1. And there is a theorem that says that the way that we do that is unique. In other words, there's no other way of expressing 60 other than this. You can rearrange the 2 and the 3 and the 5, but apart from rearrangement, that's the only way you can split 60. It's a, what do they call it? A unique factorization domain. Okay, so that's n. Okay, so if that's that, then what does that mean? Well, let's just rub this out. There is a direct formula for phi of n. Phi of n equals n times the product of all the p's of 1 minus 1 p to the I. I suppose actually to do this properly, I should put, instead of that, I'll put I is less than or equal to K. And if you have a look at this, my video Euler totient function made easy, you'll see how I go through working out 600 using this formula. So if you wanted to understand why does this formula work, well, phi of n, remember, recall phi of n. You start off with the set of, I don't know, call it x, where 1 is less than x is less than n, and the GCD of x and n equals 1. And that's the set, and then you take the cardinality of the set, or the number of elements of that set. That's what it is. So how would we work out phi of n? Well, we could use the inclusion-exclusion principle, and once again, I've got a video on that, inclusion-exclusion principle made easy. But the basic idea is that we say, well, phi of n, how would we work out phi of n? Let's say n is, we're given the formula for n up here. Well, the first thing that we do is we'd say, well, every number could possibly be, have a GCD of 1 with n, but then what we have to do is we know that P1 divides n, so we better take off all the numbers of n that are divisible by P1. And the number of numbers of n up to n that are divisible by P1 is given by this here. Okay, but we better do the same thing for the ones that are divisible by P2, and we better do it by the ones that are divisible by PK. Now the problem now is that we've counted the numbers that are divisible by, say, P1 times P2 twice. Yeah, if a number was, we'll take just the number P1, P2. I've counted it, I've taken it away. I have to take it away from this n here because it's not, it doesn't have a GCD of 1 with n. So I've taken it away here, I've taken it away here. So I've actually taken it off twice. Well, I better add back. So I'll go plus n on P1, P2. And it's the same for all these. I'm going to have to do n on P1, P3. And I'm going to have to go all the way up to taking off n on pk minus 1 times pk. But now the problem is that a number like P1, P2, P times P3, that number, I've actually taken off one more time than I should. So now, sorry, I've taken it off one time more than I should. So now I'm going to have to take off n on P1, P2, P3, and I'm going to have to do all the same thing for all these numbers that are the product of 2 primes. So I'm going to have to take off n off here, P1, pk minus 2 times pk minus 1 times pk. Okay, so this continues, and then the last thing is I'll either plus or minus n over P1, P2, dot, 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 pk. So the product of all the primes. Now, when you work that out, that just equals n times 1 minus 1 on P1, 1 minus 1 on P2, dot, 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 1 on 1 minus pk. And that, I'll leave you to expand this out if you want to see. And this is equal to n times the product. I is less than or equal to k of 1 minus 1 on pk, pi. Pi, that should be. Okay. So let's just go back. What we've done is we've proved this. And now what I'll do is I'll use this to prove this. Okay, so let's go down and do this. I might change colors just to make it a little, so we can see the distinction. So I suppose we could call this theorem if the GCD of mn equals 1, then phi of mn, it should be phi of mn equals phi m times phi n. Okay, so how would we prove that? I'll call this up here star. Okay, how would we prove that? Okay, so I'm going to let m equal, instead of using p, I'll use q. q1 to the beta 1 dot 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 ql to the beta l, and n will be as we had before, p1 to the alpha 1 dot 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 pk to the alpha k, where pi, qi are primes. In fact, this are primes. Actually, let's write it this way. The primes have to be different primes. So where are distinct primes. In other words, they're different. And qi are distinct primes. And what else do we need? Bi is an element of the natural numbers, and alpha I, the powers. These are just the powers. And here I'm letting n equal the set 1, 2, dot, 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 so we don't include 0. Okay, good. So all I've done is just define what we've got here. So an example, 600, n equals 600, and that equals, all we're saying is that equals, oh, this is going to test me, 4 times 150, so 2 squared times 150, 5 to the 1, etc., etc. I don't know. Anyway, that's what it is. There'll be a 3 there somewhere, 3 something, 3 to some power. I don't know. I'll leave you to work that out if you want. If you have problems with it, let me know. Okay, so how are we going to do this? Well, okay, we have, well, I suppose, what is phi of mn? Well, that's just phi of this number, which is q1 b1 to ql bl times p1 alpha 1 dot 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 pk alpha k. And we know there's a formula for that, the formula that we did up top in black. So how would that apply? How would that apply here? Well, I mean, Q's and P's are just primes. There's one thing we have forgotten. Okay, yeah. Okay, sorry. We have to use the fact that the GCD is equal to 1. So since GCD of mn is equal to 1, then qi does not equal pj for any ij. Okay, so what are we saying when we say that the GCD is equal to 1? Well, we're saying that there is no common divisor. So if there's no common divisor, then we can't have any prime dividing both. So I hope you can get comfortable with that line. Then, so now we can do this. Phi of mn equals phi of, I'll just write it all out, of q1 b1, beta 1, QL beta L, P1 alpha 1, PK alpha K. Now, since all of these primes are distinct, okay, so none of these primes here or here are the same. We've established that in two parts. One, when we defined M and N, we said that these primes and these primes must be distinct. And because of the GCD equaling 1, we said that when we compare any prime here and any prime here, they must be different. So all of them are distinct. So what that means is that we can just write the formula, which is, what's the formula? Well, it's Mn times the product of, well, actually, I'll write it this way because this will be better, I think. I don't want to have to relabel all the primes. So 1 minus 1 on Q1, dot, dot, dot. 1, so these are all just being multiplied. QL, 1 minus 1 on P1, dot, 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 dot. 1 minus 1 on PK. Okay, and now we can split that up. So that just equals, M was the one with all the Q's. So M times 1 minus Q1, dot, 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 1 minus QL. And we can multiply it by N then. Remember we had here M and N. I've used the M, now I'll use the N. 1 minus 1 on P1, dot, 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 1 minus 1 on PK. And what I might do is actually just put brackets around it, so you just see that. So this bit, this first bit is just 5M, and the second one is just 5N. So that proves what we wanted to prove. I suppose if I was writing a paper, I go that, thereby concluding the proof. So I'm pretty happy with that. Actually, when I did study this at university, the proof that they gave us was a lot harder than this. So I think I may have done the people watching this a favour. Okay, so I hope that's helped Behsad with his explorations of the totient function. But if he or anyone else has got a question, by all means, comment below any of my videos or drop me an email at coronahelpmathematics@gmail.com.